Welcome to EPG Pathshala. In this module, we shall discuss applications of large sample theory. Actually, in our last few modules, we have discussed asymptotic normality of sample statistics, and we have obtained asymptotic normality, asymptotic standard error, and some other types of convergences. In this module, we shall discuss applications of those large sample results in the field of hypothesis testing. For example, suppose we have a large sample from some continuous population and we require to test whether population coefficient of variation is equal to some specified value. So, since the distribution of the data is in general unknown, we adopt large sample methods, that is large sample normality of sample coefficient of variation, and use these large sample methods to develop a testing procedure for population coefficient of variation. And in the further part of this module, we shall discuss this type of applications when we have samples from more than 2 independent populations. In our last modules, we have discussed asymptotic distribution of different summary measures, and these results form the basis of developing different inferential procedures concerning different population characteristics. So, starting from a general framework, we discuss both single sample, 2 sample and multi-sample procedures and assess their performance. So, let us start with estimation in large samples. Suppose we have a large number of observations from a population indexed by the unknown parameter theta, which may be vector valued. Then one may be naturally interested in providing a good, for example, it could be some minimum variance unbiased estimator of theta. However, a good estimator is not easy to obtain, particularly when we do not have much idea about the parent population. However, if we confine ourselves to the class of estimators which are very close to the actual parameter for sufficiently large n, we can use results of large sample procedures. For example, suppose we find a sequence of estimators Tn such that the asymptotic distribution of Tn is normal with mean theta and variance sigma square. Then naturally Tn converges in probability to theta, and hence Tn is a reasonable estimator of theta for large n. Naturally, it could be possible that Tn may perform very poor in small samples. So, in statistical literature, such an estimator is said to be consistent, and we shall discuss all these things later. So, what we get from this? We get that if we have some asymptotically normal statistic, then we can also find a corresponding consistent estimator. So, this is what we intend to say. Next, suppose we are interested in testing, that is, we have some hypothesis, null hypothesis theta equal to theta naught against theta not equal to theta naught, and only a large number of observations from a population indexed by the single unknown parameter theta are available. Naturally, the usual methods like Neyman-Pearson lemma or likelihood ratio methods cannot be adopted, as the underlying population is not specified. As earlier, suppose we find a sequence of statistics Tn which is asymptotically normal with some mean theta and variance sigma square theta. Then we can at once develop a large sample procedure based on this, and that is, keeping in mind this large sample normality of Tn, a large sample procedure rejects actually can be developed which rejects the null hypothesis at an approximate level alpha if square root of n multiplied by Tn minus theta naught whole thing divided by sigma theta naught, where sigma theta is indicated as the asymptotic variance and theta is the true value, and we are just replacing theta by theta naught since theta naught is specified under the null hypothesis. If the absolute value of this statistic exceeds tau alpha by 2, we reject the null hypothesis at an approximate level alpha. Naturally, an associated confidence interval with approximate confidence coefficient 1 minus alpha is easy to obtain from the set where which is defined as absolute value of square root of n Tn minus theta divided by sigma theta less than equal to tau alpha by 2. So, just inverting this set keeping theta in the middle, we can get a random interval with coverage probability 1 minus alpha, of course in large samples. So let us illustrate the main idea using some examples. So let us start with problems regarding mean for single univariate population. Suppose n observations are available from a population with mean mu and finite variance sigma square. So first we are interested in point estimation, that is we are interested in estimating mu. Then it is known that a consistent estimator is simply x bar, provided the expected value of x bar is finite. Next comes hypothesis testing. Suppose we are interested in testing the null hypothesis mu equal to mu naught. For known sigma, one can use the statistic square root of n multiplied by x bar minus mu naught divided by sigma, and for unknown sigma we can use the statistic square root of n multiplied by x bar minus mu naught divided by s, where s is the sample standard deviation. So actually it follows from Slutsky theorem that under certain conditions s converges in probability to sigma, and therefore asymptotically the statistics square root of n x bar minus mu naught by sigma and square root of n multiplied by x bar minus mu naught by s are equivalent. However, if sigma is unknown, we need to use the latter statistic. So for large n, each variable has a standard normal distribution under the null hypothesis, and hence a large sample test can be constructed using this statistic. Our next problem, actually after performing some test of hypothesis, it is natural to consider confidence interval estimation. So first of all, assume that sigma is unknown, and therefore to get a confidence interval for mu, we start from the relation, actually approximate relation, that probability that absolute value of square root of n multiplied by x bar minus mu by s less than equal to tau alpha by 2 is approximately equal to 1 minus alpha. And then proceeding in an obvious way, we arrive at the random interval with endpoints x bar minus tau alpha by 2 multiplied by s by square root of n and x bar plus tau alpha by 2 multiplied by s by square root of n with approximate coverage probability 1 minus alpha. Therefore, we get some random interval having approximate coverage probability 1 minus alpha, and therefore using large sample techniques we arrive at a confidence interval with desirable coverage probability, at least for large n. So our next problem is the problem regarding variance for single univariate population. So we start with point estimation. Suppose we are interested in estimating sigma square or sigma, that is population variance or population standard deviation. Then consistent estimators are simply sample variance s square, which is defined as 1 by n summation x r minus x bar square, and all these are proved earlier that s square and s are consistent for sigma square and sigma respectively. So these are good estimates, at least in large sample, for the mentioned parameters. Next comes hypothesis testing. Suppose we are interested in the null hypothesis sigma equal to sigma naught. Assume mu is unknown and parent distribution is normal. Then we use either square root of 2n multiplied by s minus sigma naught divided by sigma naught, or square root of, or the statistic square root of n by 2 multiplied by s square minus sigma naught square divided by sigma naught square, which are asymptotically normal 0 1 under the null hypothesis. So in the first case, for the first statistic, we have used the large sample distribution of sample standard deviation, and for the second statistic we have used the large sample distribution of the sample variance, but each have some asymptotically normal distribution under the null hypothesis. Hence large sample tests can be constructed as given earlier. However, if the parent distribution is not normal, then the variance, the asymptotic distribution, the variance of the asymptotic distribution is different from sigma square. So actually for non-normal parent, we have the result that the large sample distribution of M2, that is second order central moment, is asymptotically normal with mean mu2, and variance which is denoted by tau square is defined as mu4 minus mu2 square. And since M2 is a consistent estimator of mu2, we can use the statistic square root of n multiplied by m2 minus sigma naught square, that is the value specified under the null hypothesis, divided by tau hat, where tau hat is a consistent estimator of tau. Naturally, such a statistic by Slutsky's theorem is again asymptotically standard normal, and hence tests can be constructed as earlier. Using either statistic, one can construct the confidence interval with approximate coverage probability 1 minus alpha. Next, consider two independent populations, that is two independent univariate populations, and our interest is to provide some testing procedure for means. Suppose ni observations are available from a population with mean mu I and finite variance sigma square I. Assume that the two populations are independent. So, for the difference of means, that is mu1 minus mu2, a consistent estimator is simply x1 bar minus x2 bar, that is the difference of the sample means. Next, suppose we are interested in testing, that is we are interested in testing mu1 minus mu2 equal to mu naught. If sigma is unknown, one can use the statistic Tn defined by x1 bar minus x2 bar minus mu naught whole thing divided by square root of sigma 1 square by n1 plus sigma 2 square by n2. If we assume that the ratio n1 divided by n1 plus n2, if we assume that the ratio n1 divided by n1 plus n2 tends to lambda, which belongs to an open interval 0 1, and the ratio n2 divided by n1 plus n2 obviously approaches 1 minus lambda, then it follows that square root of n1 plus n2 multiplied by the vector with components x1 bar minus mu1 and x2 bar minus mu2 is bivariate normal with mean 0, and dispersion matrix as a diagonal matrix with elements sigma 1 square divided by lambda and sigma 2 square divided by 1 minus lambda. Thus, under the null hypothesis, Tn is asymptotically standard normal, and hence large sample tests can be constructed. Next, consider the case when sigma is are unknown. Naturally, if sigma is are unknown, we replace them by their consistent estimates Si square. Then, applying Slutsky's theorem, again the modified estimator Tn dash, which is defined as x1 bar minus x2 bar minus mu naught whole thing divided by s1 square by n1 plus s2 square by n2 is asymptotically normal, and hence tests can be constructed using this Tn dash. In addition, considering x1 bar minus x2 bar minus mu divided by square root of s1 square by n1 plus s2 square by n2 as a pivot for mu, one can find an approximate confidence interval, and the expression is given in the text, obviously with approximate coverage probability 1 minus alpha. Next, consider the problem regarding the variance for two univariate populations. As earlier, suppose ni observations are available from a population with unknown mean mu I and finite variance sigma I square, and we assume that the two populations are independent. Then, for sigma 1 plus sigma 2 or sigma 1 by sigma 2, a consistent estimator is simply s1 by s2, and if we are interested in testing sigma 1 square minus sigma 2 square equal to 0, then for normal parents we can use the fact that square root of ni multiplied by si square minus sigma I square converges in distribution to a normal distribution with mean 0 and variance 2 sigma I square, and independently for each I. So, we can construct our statistic Tn as s1 square minus s2 square whole thing divided by 2 sigma to the power 4 divided by n1 plus 2 sigma to the power 4 divided by n2, where sigma square is the common unspecified value under the null hypothesis. Thus, we replace sigma square by its pooled estimator s square, which is defined as n1 s1 square plus n2 s2 square divided by n1 plus n2, and since under the conditions that n1 divided by n1 plus n2 and n2 divided by n1 plus n2 converges to a finite quantity belonging to the open interval 0 1, s square is consistent for sigma square, and hence we can replace sigma to the power 4 by s to the power 4 in our original statistic to get our modified statistic, which again asymptotically is standard normal, and hence under the null hypothesis, and hence we can perform large sample tests using this statistic. As earlier, consider testing in using SI, that is sample standard deviations. Actually we have considered hypothesis that sigma 1 square equal to sigma 2 square, which can equivalently set as sigma 1 equal to sigma 2, and one can use the large sample distributions of S1 and S2 to get another large sample test for the same hypothesis, and this can be found in our presentation. Next, suppose we are interested in finding some inferential procedure for population coefficient of variation. So, as earlier, suppose n observations from a normal population with unknown parameters are available, denote the population coefficient of variation and sample coefficient of variation by V and small v respectively. Naturally, a consistent estimator of capital V is small v. Suppose we want to perform a test for the null hypothesis V equal to V naught, then looking at the fact that the large sample distribution of sample coefficient of variation is normal with mean 0 and variance as given in the text, we can use a standardized statistic and we can replace the unknown capital V, that is unknown population coefficient of variation, by V naught as specified by the null hypothesis, which has a normal distribution, of course in large sample. So, we reject the null hypothesis if Tn such a statistic Tn exceeds tau alpha or less than minus tau alpha, or the absolute value of Tn exceeds tau alpha by 2, according as the alternative is V greater than V naught or V less than V naught or V not equal to V naught. So, as earlier, we can find an approximate confidence interval for V starting from the relation as given in this, and finally one can get the approximate confidence interval which can be seen in our text. Next, we pass on to some interesting context. We shall give some large sample test for normality. Actually, if the distribution of the underlying data comes out as normal, then most of the problems are satisfied because we can use the usual methods using normality. So, suppose in IID observations from a population with finite moments up to order 8 are available. Often we are interested in testing the null hypothesis that the underlying distribution is normal. Suppose gamma 1 and gamma 2 are respectively the coefficient of skewness and kurtosis, then it is well known that for normal parents gamma 1 equal to 0 and gamma 2 equal to 0. Thus, we can perform test of normality via the null hypothesis gamma 1 equal to 0 and gamma 2 equal to 0. For testing the first hypothesis, that is gamma 1 equal to 0, we use the statistic square root of n by 6 multiplied by g1, which is asymptotically standard normal under the null hypothesis. However, for testing the second null hypothesis, that is gamma 2 equal to 0, we use the statistic square root of n by 24 multiplied by g2, which again is asymptotically standard normal under the null hypothesis. For making the first test, n equal to 30 is sufficient to reach normality, whereas for the second test n equal to 200 ensures normality. But these are tests for skewed and symmetric alternatives, and hence one can consider the combined hypothesis, that is the joint hypothesis that gamma 1 equal to 0 and gamma 2 equal to 0. Then an obvious statistic is n times g1 square divided by 6 plus n times g2 square divided by 24, which under the null hypothesis is distributed asymptotically as a chi-square distribution with 2 degrees of freedom. Next, we come to another interesting aspect, which is known as variance stabilization. So, the first question is, why to stabilize the variance? What is this? Suppose IID observations from k populations indexed by parameters theta I are available. Suppose a consistent estimator TIN separately for k populations are available, then often the asymptotic variance sigma square theta I depends on theta I, and we need to replace them by consistent estimates for making a test. Such substitution makes the convergence slower. Actually, in that case, we need asymptotic normality as well as convergence in probability for a consistent estimate of sigma square theta I. So, naturally, such substitution makes the convergence very slower. Thus, it would be better if we can use some transformation to make the asymptotic variance independent of the parameter, so that we need not to plug in that case some estimates for the unknown variance. Thus, this means we need some transformation h of t for some continuous function h with a non-zero derivative at theta, such that the asymptotic variance which is already derived as the first derivative of h at theta whole square multiplied by sigma square theta is independent of theta. Hence, we need to decide h in such a way that this asymptotic variance is a constant, that is this asymptotic variance equal to c square for some c independent of theta. Thus, h must satisfy the differential equation that first derivative of h at theta equals c divided by sigma theta, so that h can be determined up to a change of origin and scale. So, let us quickly give some examples. So, first example is regarding binomial proportion. Suppose xi are IIT binomial 1p variables, then it is well known that the large sample distribution of x bar is asymptotically normal with variance p into 1 minus p. We are looking for some transformation say h of x bar such that the asymptotic variance is independent of p. Then from the relation as discussed before, hp is nothing but c times integral of 1 by square root of p into 1 minus p plus k, which on integration gives the expression that hp equal to 2c times sine inverse square root of p plus k. Now, choosing c equal to 0.5 and k equal to 0, we get the transformation, that is angular transformation for binomial proportion given by sine inverse square root of p. Next comes the Poisson mean. Suppose xi are IIT Poisson theta variables, then it is well known that large sample distribution of x bar is again normal with variance theta square, and we are looking for some transformation making asymptotic variance independent of theta. So, from the differential equation as we have formed, we get h theta as 2c times square root of theta plus k. Now, choosing c equal to 0.5 and k equal to 0, we get the transformation h theta as square root of theta. Next, we proceed to normal variance. Suppose xi are IID normal with mean mu and variance sigma square, then the large sample distribution of s square is normal with mean 0 and variance 2 sigma to the power 4. As earlier, we need some transformation for making this asymptotic variance independent of sigma square, and solving the differential equation, we get h of sigma square equal to c divided by square root of 2 multiplied by log sigma square plus k, and choosing c equal to square root of 2 and k equal to 0, we get the transformation log of sigma square. And our next candidate is correlation coefficient. We have already derived that for bivariate distributions with correlation coefficient rho, and if in particular the bivariate distribution is bivariate normal, then for sample correlation coefficient r, square root of n r minus rho converges in distribution to a normal distribution with variance 1 minus rho square whole square. So, as earlier, if we need some function h making asymptotic variance independent of the parameter, we have to solve the differential equation h rho, that is the differential equation as given earlier, and performing the solution and integration, we find that h rho comes out as half log of 1 plus rho divided by 1 minus rho, which can be equivalently expressed as tan hyperbolic inverse rho, and this particular transformation is very important in statistical literature and is known as Fisher's jet transformation. Next, we shall discuss another interesting aspect, that is convergence rate of the variance stabilized transformation. Actually, we have argued that variance stabilization makes the convergence faster. So, let us consider using some examples. The greatest advantage of variance stabilizing transformations is that normality is reached more rapidly than the original statistic. As an example, consider Fisher's jet transformation. It is already noted that the large sample distribution for R is normal. Then from Slutsky theorem, it follows that T1n defined by square root of n multiplied by r minus rho divided by 1 minus r square is standard normal in large samples. Again, for Fisher's jet transformation, T2n defined by square root of n multiplied by tan hyperbolic inverse r minus tan hyperbolic inverse rho converges in distribution to standard normal. Thus, for comparison, we conduct a simulation study with bivariate normal distribution having correlation coefficient rho and provide a histogram together with the normal density plot for both the variables for different choices of n and rho. All this can be found in the next pages. In the first page, you can find the histograms for the variable t1 for n equal to 150 and rho as minus 0.6, 0.3 and 0.7. In the second page, you can find the corresponding histograms and the normal density for the statistic T2. So, what we get? It is observed that for both the variables, the convergence to normality is reached for rho near 0. The transformed variable converges at a faster rate. However, for very large and very small values of rho, the convergence to normality is not seen even for n equal to 150 for the original and for n equal to 100 for the transformed. In particular, for rho nearby plus minus 1, the distribution is quite different from standard normal even for large n. So, in a simulation study, we have also seen how the convergence rate is varying for different values of n and compared with some untransformed variable. In our next module, we shall discuss something different. First, we start with the applications of jet transformation for k bivariate normal populations and then proceed to Pearsonian chi-square. That is the large sample procedure when the data is presented in the form of frequencies. So, all these things, the large sample distribution and their applications, all this will be discussed in our next module.